Students, in today's video we will discuss about the forging process, and the main contents are forging design, forging defects, and the forging analysis. So first of all we will discuss the forging die design. As you know, the dies are being used in the forging, and if we are considering the impression die forging, then we know that we have to use the two dies, and lower die and upper die. You can say here this is the lower die and this one is the upper die, and this is the cavity space between these two dies, and here the material is flowing. Now certain design factors we have to consider, like you can see here, a certain amount of extra space has to be provided, and this extra space is called gutter, because the extra material, which is called flash, it will be flowing between these two dies. Whenever these two dies are closing, then the extra material will be flowing between this gap, you can say here. So this extra material is called the flash. This is called flash. So to accommodate this flash, we have to provide certain additional space, and that is called gutter. Now you can see these walls are not perfectly vertical. You can see here certain amount of slantness is there. We can say here these walls are not perfectly well, and these are certainly inclined. So these are called the draft angle. It may be internal or it may be outside, and these are provided so that the after forging process we can remove the job very easily. Now next you can see these are the fillets, these are the corners. Why we are providing these type of radii? Because the best design is that never leave any sharp corner in the die design, otherwise there will be a problem of cracks and other type of difficulties. So we'll discuss further. So as discussed here, I have already explained that we are not leaving these walls as a perfectly vertical. We are giving certain inclination. So if we are giving inclination in the inside, then it is called the internal draft, you can see, and at the external surfaces we can define at the external draft. So that why we are providing, as already explained, the job, whenever the job will be removed after forging, it will be removed very easily. Well, now let us suppose what consider if these walls are perfectly vertical and the job is there. So what will happen when this job is to remove? There will be difficulty to remove the job from this die. So that is why we have to provide the draft. Now fillet and corner radii. Fillet are the internal radii, you can say, and corner are the outside corner radii, and we have to provide these radius. Okay, we are not providing like sharp corner like this. So this is called fillet radii and corner radii. Next is the shrinkage and die wear allowance. Shrinkage and die wear allowance. Die cavities are made correspondingly larger by using the shrink rule. As we know, the material is heated in the forging process. So after heating it will expand, then it will shrink. That is why to accommodate this expansion of the heating, we have to provide certain extra space, that is called shrink wear. And next is the die wear allowance. In die wear allowance, you can see that from one die you can make 100 or 1000 components. But if you are making 100,000 components, definitely there will be certain amount of wear associated with the die surfaces. So the die surfaces will be wear out. That is why we have to provide certain extra material in the die so that we can compensate this wear. So the correct range we can define here, the 0.4 to 0.8 mm up to 45 Newton. Forging this extra length we have to provide as a die wear allowance. Flash and gutter is already being explained. Now the mismatch. If the two dies are not perfectly aligned, then what will happen? You will not get exact shape and size of the forging. So this kind of shift is the side shift. This kind of the shift is the end shift. These two diagrams are showing that the two dies are not perfectly matched together. And this is the true alignment. This type of design we want. This is not desirable. Next we will discuss about the forging load calculation. As you can see here, the total energy required for forging can be categorized into three type of portion or three categories. First one is ideal when no friction is considered. Second one is the energy when the friction is considered. and third one is redundant, when energy is applied for the forging but there is no change in the shape of the object is happened. So sum up of these three energies is called the total energy required for forging. Now first of all, in a first category, when the forging load is applied and we have to calculate the forging force, so it's very simple. We can calculate it by multiplying the stress, yield stress of the material and cross sectional area of the material where the forging force is being applied. So this is a very simple calculation. Next category is plane strain forging when friction is being considered. Let us suppose there are the three stresses, sigma 1, sigma 2 and sigma 3 principal stresses, and associated principal strains are epsilon 1, 2, 3. And in plane strain condition, we are assuming the strain 0 in one direction. So we are assuming in this particular analysis that our width remain constant. So the strain in the direction of the width remain constant. Strain will be equal to 0 as the width remain constant. So there is no change in the length of the width, we can say. So there is no change in the width. So the strain in that particular direction of the width will be equal to 0. In this diagram, you can see here, this is the rectangular job. B is the width, L is the length, and this job is being placed here between these two dies. This is the upper die, this is the lower die. Now what will happen when these two dies are getting close together? So the compressive stress will be acting on this job. So we are assuming here one elementary area here at a x distance from the center line, you can see. From center line you can see at the x distance we are considering this elementary area. So compressive force P is acting, okay, and the material will flow lateral in a lateral direction very freely. So the longitudinal stress will be acting in the particular longitudinal direction, that is we can assume sigma x plus d sigma x and sigma x. And as you know that the material is sliding between these two dies, so there will be a frictional shear stress tau x which is acting in opposite direction of the material movement. The material is moving in this direction, the frictional stress tau x will be moving in the opposite direction. So you can see basically there are two principal stresses which are acting. First one is the sigma x, okay, this is the sigma x, and this is the sigma x, and another is a compressive stress P which is acting. So we have to apply the Tresca yield theory for determination of the compressive force during forging operation. And in Tresca theory we know this formula, sigma 1 minus sigma 3 is equal to sigma naught. So sigma 1 is the major stress, sigma 3 is the minor stress, sigma naught is the yield stress of the material, which may be varying. It is depending on the material. So in this case we know sigma 1 is equal to sigma x, sigma 3 is equal to compressive stress, it's negative direction. So sigma x plus P is equal to sigma naught. This formula is very important formula which is being utilized for the derivation of calculation of the forging pressure. Now after derivation, the final formula to calculate this P is this. P is the forging pressure, or we can say the stress, forging compressive stress we can say. So P is equal, we can calculate by this formula, P upon 2K, K is the shear yield stress, or we can say the yield stress in shear K, and sigma naught is the yield stress in the material. So this formula comes exponential 2 mu upon h into L minus x. This is the multiplication. So 2 mu upon h into L minus x. So you can say mu is a constant which is coefficient of friction between die surface and the job. H is the thickness of the job, it is also constant. L is the length, L is considered from center distance to end in this diagram, and x is the variable. X is varying from it is measured like x may be vary, x is x equal to 0 at the center, it is maximum at the end. So it will be varying. So from this formula we can calculate the sigma x value, which is our longitudinal stress, principal stress, and P minor stress, which is called compressive stress, and we can plot this stress diagram over this particular length of section of the forging. So first of all we will calculate our compressive force, that is P. Compressive stress, we can say force can be calculated easily if we are calculating the stress. So first category of first case we are considering at x is equal to L, which is called end surface. It means that in our section at center x is equal to 0 we are assuming, and at x is equal to L this point is there. So if we are putting x is equal to L in this formula, then x is equal to L, so L minus L, so it's equal to 0. So exponential 0 will be equal to 1, so P will be equal to sigma naught at the end surface. So we can plot here P is equal to sigma naught at the end surfaces here. So at x equal to L, x is equal to L, P will be equal to sigma naught. So after calculating the compressive force at the compressive stress at the end surface, we can calculate the compressive stress at the center also. So at the center we know x is equal to 0. As you can see here at the midpoint x is equal to 0, that we are assuming at the center point. So at x is equal to 0, if we are putting in this formula, so this formula will become P is equal to sigma naught exponential 2 mu L upon h, because x is equal to 0. So at the center point the value will become this, and it will be like this value. So this value is total sigma naught multiplied by exponential 2 mu L upon h. So we can plot this point and we can make this curve like in this manner, you can say. So this is the variation of the compressive stress along the length of the forging. Okay. Now in second stage we have to calculate the value of the sigma x or longitudinal stress. So we will use these formulas also for calculation purpose. So variation of the sigma x we have to determine at x is equal to L. We know that P is equal to sigma naught. Why? As from this earlier formula, P is equal to sigma naught e की power exponential we can say 2 mu L minus x upon h, you can say. So at x is equal to L, this term will be equal to 0, so P is equal to sigma naught. So when P is equal to sigma naught, by Tresca theory we can say sigma x plus P is equal to sigma naught. So P is equal to sigma naught, if we are putting here, then we will get the sigma x is equal to 0. So at the end surface, the longitude, or we can say at the end surface of the job, the longitudinal stress is equal to 0. This value is equal to 0. Sigma x is equal to 0. Now we have to calculate the sigma x value at the center point. At the center point we know that at the center point P is equal to sigma naught, earlier calculation we have done, exponential 2 mu L upon h. So this is the value of the compressive stress at the center. This value we have calculated here. So by applying Tresca theory, the Tresca theory sigma x plus P is equal to sigma naught here applied here. So we can calculate the sigma x. So sigma x will be equal to sigma naught minus P. So P value will be put it here. So finally the result will come here. So expression will come here, sigma x is equal to sigma naught 1 minus exponential 2 mu L upon h. So this value will be plotted here. This value will be somewhat lower as compared to sigma naught e की power 2 mu L upon h. So you can join this diagram, these points with the help of this curve. So this is the variation of the longitudinal stress, and this is the variation of the particularly compressive stress. This is a friction L diagram also said. Next we will discuss the forging defects. There are various type of forging defects in the job. First one we will discuss about the unfilled section. You can see here in diagram there are certain sections which are unfilled. The material is not able to penetrate air, material not able to flow air, and this type of defects are called the unfilled section. And this is the forging defect. We can say we are not getting it designed because material is not able to flow. It may be happen because of the insufficient pressure, forging pressure, or it may be possible that the faulty design of the die. Next is the cold shut or cold or small cracks. As you can see in pictorial diagram, these are the cracks which are obtained. So this is happening due to the small corner and small fillet radii. So why this is happening, we can simple study by detailed diagram. This is the upper die, top die, bottom die. These are the cavity spaces you can see here. And there are the two cases when we are leaving the very small fillet to small corner, and when we are giving the sufficient type of fillet or sufficient type of radii of the fillet. Now whenever this job is getting pressed, whenever load is being applied, then what will happen? this material does not follow the sharp corner. This material will flow ahead. While whenever we are leaving this particular radius, then material will be able to flow very smoothly. Further, what will happen? Flow into die fails to follow sharp corner. The material will move ahead while these corners are left. Here the material will flow, but gradually these corners will be filled up. So we can say here in fourth stage you can see the metal reaches bottom of the cavity before filling section. The material is flowing here. Material is flowing here, but this corner point is left. Here corner points are left, but subsequently they will get filled up. Now what will happen after forging? What will happen? There sometime what will happen? This material will flow back. When there is no space to flow, the material will flow back. When material will flow back, these small fillet radii corner will get filled very easily, but these type of points will be left, and due to small corner there is a high stress concentration, so cracks may get formed. So here cracks may get formed, here cracks will not get formed. These type of defects are called cold shut defects. Next defect is scale pits. Scale pits are obtained whenever you are utilizing one die for making certain jobs. So the scales and burnt layers are left inside the die surface, and when further jobs are processed in the forging, these type of scale or impurities will get embedded into the job surface, and due to which the scale pits and small type of irregular depressions are formed, and these are called the scale pits. Next is the die shift. When your dies are not properly aligned, then what will happen? These dies are not properly aligned, so you will get the faulty job. Another is flags and improper grain flow. Flags are happening due to the improper cooling. As you can say that your job is like that, and that external surface the rate of cooling is higher, but internal surface rate of cooling is not there. So it will be subjected to cooling stress and thermal stress, we can say. Due to thermal stresses, cracks may happen in internal surfaces, so internal rupture may occur. Next is improper grain flow. When material is flowing in particular direction, but there is not proper flow, there is improper flow, due to which we will not obtain the grain orientation as per desire. So that is called the improper grain flow. So these are the sufficient from here, and thank you very much for listening. Thank you very much.